Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're simply the kind of person who likes drifting off to sleep while contemplating the vast mysteries of the cosmos rather than counting sheep. Either way, you're in exactly the right place. Tonight's journey takes us to one of the most dramatic and violent processes in the universe, and yet one that unfolds with such slowness that it becomes almost peaceful when viewed from the proper perspective. We're going to explore galactic cannibalism, the process by which galaxies devour one another across billions of years. Before we begin our cosmic voyage, if these gentle explorations of the universe help you unwind at the end of your day or give you a quiet space to let your thoughts drift, consider liking this video and subscribing to the channel. It helps other sleepy souls find their way here, one peaceful night at a time. Now, let's dim the lights and begin. When you look up at the night sky and see the soft band of the Milky Way stretching across the darkness, you're witnessing something that appears eternal and unchanging. The stars seem fixed in their ancient patterns. The galactic disk a permanent structure that has always been and always will be. But this perception is an illusion created by the vast difference between human timescales and cosmic ones. The truth is far more dynamic, far more violent, and far stranger than those quiet stars suggest. Our galaxy is a cannibal. It has been consuming smaller galaxies for billions of years, and it will continue to do so for billions more. Right now, at this very moment, the Milky Way is in the process of tearing apart and absorbing several smaller companion galaxies. The stars you see scattered across our galactic halo, those ancient wanderers that orbit far above and below the main disk, many of them are immigrants. They were born in other galaxies, in systems that no longer exist as separate entities because the Milky Way pulled them apart, swallowed their stars, and scattered their remnants across space. Galactic cannibalism is not some rare cosmic accident. It is, in fact, one of the primary mechanisms by which galaxies grow and evolve. In the early universe, when matter was more densely packed and galaxies were closer together, these cosmic collisions and mergers were far more common than they are today. The beautiful spiral galaxies we observe, the massive elliptical galaxies that dominate galaxy clusters, the peculiar and irregular galaxies with their distorted shapes. Almost all of them bear the scars and signatures of past mergers. They are composite structures, built from the wreckage and remains of countless smaller systems that fell into their gravitational embrace and were consumed. Tonight, we'll journey through this process in exquisite detail. We'll explore how galaxies collide, what happens during these encounters, and why they look so different from what you might expect. We'll visit the Milky Way's own violent past and see the evidence of ancient mergers still visible in the motion and chemistry of stars around us. We'll look forward to our future collision with the Andromeda Galaxy, an event already set in motion, already inevitable, though still billions of years away. And we'll understand how these violent cosmic events, paradoxically, help create some of the most beautiful structures in the universe. The word cannibalism might sound harsh, almost cruel, but in the context of galaxies, it's simply the way things work. Gravity is patient and relentless. When two galaxies wander close enough to feel each other's pull, there is no escape. The dance begins, slow and inexorable, lasting hundreds of millions or even billions of years. And when it's finished, what emerges is something new, something changed. A galaxy that carries within it the memory of everything it has consumed. So settle back, let your breathing slow, and your body relax. Let the weight of the day drain away. Tonight, you are floating through the universe, watching galaxies collide and merge across vast expanses of space and time. You're witnessing the slow-motion violence that shapes cosmic structure. You're seeing how the universe builds its largest objects through endless acts of consumption. And in this grand cosmic process, violent though it may be, there is a strange kind of peace. A rhythm that plays out across billions of years, far beyond the reach of worry or hurry. Let's begin our journey into the realm where galaxies devour each other. The nature of galactic collisions. When we speak of galaxies colliding, it's important to understand what we actually mean, because the reality is quite different from what most people imagine. You might picture two solid objects smashing into each other, stars exploding, worlds being destroyed in catastrophic impacts. But galaxies are not solid objects. They are, in many ways, more like clouds than like rocks. Vast clouds of stars, yes, but clouds nonetheless. Structures where the actual solid matter is separated by enormous distances. Consider the scale involved. The Milky Way contains somewhere between 200 and 400 billion stars, spread across a disk about 100,000 light-years in diameter. That sounds incredibly crowded until you realize just how much empty space lies between each star. Our nearest stellar neighbor, Proxima Centauri, is more than 4 light-years away. That's about 25 trillion miles. If you were to shrink the Sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand about 10 miles away. The space between stars is almost perfectly empty. This means that when two galaxies collide, the stars themselves almost never actually hit each other. The probability of a direct stellar collision during a galactic merger is vanishingly small. Instead, what collides are the gravitational fields of the galaxies. Each galaxy is surrounded by an invisible web of gravitational force, extending far beyond its visible edges. And it is these gravitational fields that interact first, pulling at each other, distorting each other, creating tidal forces that begin to reshape both systems long before they physically interpenetrate. Imagine two enormous spirals approaching each other through space. They are moving at hundreds of kilometers per second, yet at galactic scales, this is almost painfully slow. As they draw closer, separated by perhaps a few million light-years, they begin to feel each other's gravity. The mutual attraction accelerates both galaxies toward each other. The pull is gentle at first, but it grows stronger with every passing million years. As the distance shrinks, tidal forces come into play. These are the same kinds of forces that create ocean tides on Earth, where the gravitational pull is stronger on one side of an object than the other, creating a stretching effect. In the case of galaxies, the stars on the near side of each galaxy feel a stronger pull toward the other galaxy than the stars on the far side. This differential force begins to distort the galaxy, pulling them out of their original shapes, stretching them like taffy. The first passage might happen when the galaxies are still separated by hundreds of thousands of light years. They sweep past each other, neither fully penetrating the other's disk, but the gravitational interaction is enough to create disturbances. Spiral arms become twisted. Stars are pulled out of their orderly orbits. Gas clouds are compressed by the tidal forces, and in these compressed regions, new stars begin to form rapidly, lighting up both galaxies with bursts of blue-white light. After the first passage, the galaxies continue moving apart, but they have lost some of their kinetic energy to the interaction. Their mutual gravity has acted like an invisible rope, slowing them down, ensuring that they cannot escape each other. They reach a maximum separation, perhaps 1,000,000 light years or more, and then gravity begins to pull them back together again. The second passage will be closer, more violent, more distorting than the first. This dance can continue for billions of years, multiple passes, each one closer than the last, each one more destructive to the original structures. The spiral arms become more and more distorted. Long tidal tails stretch out into space, great arcing streams of stars pulled from the galaxies by tidal forces. These tails can extend for hundreds of thousands of light years. Graceful curves painted against the darkness of intergalactic space. Eventually, after perhaps a dozen passes, the two galaxies lose enough orbital energy that they can no longer pull apart. The final merger begins. The cores of the galaxies spiral toward each other, sinking through the combined mass of stars and gas. This process, called dynamical friction, acts like a cosmic brake, gradually robbing the galaxy cores of their remaining orbital energy. The cores spiral inward in tighter and tighter circles until, finally, they merge into a single structure. What emerges from this billion-year collision is something entirely new. The original spiral structures are usually destroyed. The orderly, rotating disk of stars becomes chaotic, with stars moving in random directions on elliptical orbits. If both galaxies were large spirals, the merger often produces an elliptical galaxy, a huge ball of stars with no disk, no spiral arms, just billions of stars moving on complex orbits around a common center. But here's the crucial thing to understand. Despite all this cosmic violence, despite galaxies being torn apart and merged into new structures, the individual stars are almost always fine. They simply find themselves in new orbits, in a new galaxy, surrounded by new neighbors. A star that formed in one galaxy billions of years ago might end up, after a merger, orbiting in what is now a completely different type of galaxy, perhaps trillions of miles from where it started, but otherwise unchanged. The star itself knows nothing of the grand drama it has been part of. The gas in the galaxies, however, does collide. Unlike stars, which can pass through each other's galaxy without touching, the diffuse clouds of gas and dust that fill the space between stars can and do run into each other. When giant molecular clouds collide at hundreds of kilometers per second, they create shock waves that compress the gas, cooling it and causing it to collapse under its own gravity. This triggers massive bursts of star formation. Galaxies that are merging can form new stars at rates 100 times faster than isolated galaxies, creating what astronomers call starburst galaxies. These starbursts light up the merging galaxies like cosmic fireworks. The new stars are predominantly hot, massive, and blue, burning through their fuel at prodigious rates. They don't live long, these massive stars. Within a few million years, they explode as supernovae, adding even more energy to the chaos of the merger. The combined light from millions of these new stars can make merging galaxies some of the brightest objects in the universe, visible across billions of light years. There is another component to galaxies that plays a crucial role in these collisions, one that we cannot see directly but whose influence is unmistakable. Dark matter. Every galaxy is surrounded by a vast halo of dark matter, extending far beyond the visible stars. This dark matter contains most of the galaxy's mass, and it is the gravitational pull of these dark matter halos that really drives galactic mergers. The dark matter halos merge first, long before the visible parts of the galaxies come together, creating a gravitational framework within which the stars and gas are pulled together. Understanding galactic collisions means understanding that we're watching a process that unfolds across timescales that dwarf human comprehension. A single galactic merger might take 2 or 3 billion years from first approach to final coalescence. That's longer than complex life has existed on Earth. Entire species rise and fall. Continents drift across planetary surfaces. Stars are born and die, all while two galaxies slowly, inexorably merge into one. Types of galactic cannibalism. Not all galactic encounters are created equal. The universe presents us with a rich variety of merger types, each producing different outcomes depending on the sizes, shapes, compositions, and relative velocities of the galaxies involved. Understanding these different types of interactions helps us piece together the evolutionary history of galaxies and predict their futures. The most dramatic type of encounter is what astronomers call a major merger. This occurs when two galaxies of roughly similar size collide. The classic example that everyone knows is the future collision between the Milky Way and Andromeda. Both are large spiral galaxies containing hundreds of billions of stars, and when they merge, roughly 4.5 billion years from now, neither galaxy will dominate. Instead, they will tear each other apart and rebuild themselves into something entirely new. Major mergers are spectacular events. The two galaxies orbit each other multiple times, their spiral structures becoming increasingly distorted with each pass. Long tidal tails stream out into space, great arcs of stars that can extend for hundreds of thousands of light years. The cores of both galaxies, each containing a supermassive black hole, spiral toward each other, destined eventually to merge into a single, even more massive black hole. The gas in both galaxies collides and compresses, triggering intense bursts of star formation that can create billions of new stars in just a few million years. The result of a major merger between two spiral galaxies is usually an elliptical galaxy. The original orderly rotation of the spiral disks is destroyed, converted into random motion through a process called violent relaxation. The stars end up moving on chaotic orbits, some plunging through the center, others swinging out to great distances, creating the smooth, spherical appearance of elliptical galaxies. These newly formed ellipticals often have very little gas left, most of it having been either converted into stars during the merger or blown out of the galaxy by supernovae and stellar winds. But major mergers are not the only way galaxies interact. In fact, they're not even the most common. Far more frequent are what astronomers call minor mergers, or galactic cannibalism proper. This is what happens when a large galaxy encounters a much smaller one. The mass ratio might be 10 to 1, or 100 to 1, or even 1,000 to 1. In a minor merger, the smaller galaxy doesn't stand a chance. As it approaches the larger galaxy, tidal forces begin to pull it apart. Stars are stripped from its outer regions, stretched into long streams that wrap around the larger galaxy. If the dwarf galaxy contains gas, that gas is stripped away even more efficiently than the stars, falling into the larger galaxy where it can fuel new star formation. The process is surprisingly swift in cosmic terms. A dwarf galaxy falling into the Milky Way might be completely shredded and absorbed in just a few billion years. What remains is a stellar stream, a river of stars following the original orbit of the dwarf galaxy, gradually spreading out and mixing with the larger galaxy's halo. Eventually, even these streams disperse, and the stars become indistinguishable from stars that formed in the larger galaxy. The dwarf galaxy's identity is erased, its stars absorbed, its history preserved only in the chemical signatures and orbital characteristics of its former members. The Milky Way is currently consuming several small galaxies in exactly this way. The Sagittarius dwarf elliptical galaxy is perhaps the most prominent example. This small system is being torn apart right now, its stars stretched into a stream that loops around the Milky Way multiple times. The Large and Small Magellanic Clouds, those two dwarf galaxies visible from the southern hemisphere, are likely also on their way to being consumed, though that process will take billions of years to complete. Astronomers also distinguish between wet mergers and dry mergers. A wet merger involves at least one galaxy that is rich in gas. When these galaxies collide, the gas clouds run into each other, creating shock waves that compress the gas and trigger intense star formation. Wet mergers are messy, dramatic affairs, lighting up the universe with the combined glow of billions of newly formed stars. Dry mergers, by contrast, involve gas-poor galaxies, typically old ellipticals that have already used up most of their star-forming material. When two elliptical galaxies merge, there's relatively little star formation. Instead, the merger simply adds the stellar populations of both galaxies together, creating an even larger elliptical. The process is still violent in gravitational terms, with stars having their orbits dramatically altered, but it happens without the spectacular fireworks of starburst activity. There's another type of interaction called galaxy harassment. This occurs in dense environments like galaxy clusters, where hundreds or even thousands of galaxies are packed into a relatively small region of space. In these crowded neighborhoods, galaxies constantly experience close encounters with their neighbors. Each encounter on its own might not be particularly dramatic, but the cumulative effect of many such interactions can be profound. A small galaxy in a rich cluster might experience dozens of close encounters over a few billion years. Each encounter strips away a little more of its gas, distorts its structure a little more, heats up its stellar orbits a little more. Over time, galaxy harassment can transform a spiral galaxy into a spheroidal or irregular galaxy, changing its shape and shutting down its star formation. The galaxy becomes a victim of its environment, slowly beaten down by repeated gravitational encounters. The outcome of any galactic encounter depends on many factors. The relative masses of the galaxies matter enormously. So do their relative velocities and their impact parameter, the distance of closest approach. The orientation of their disks affects how efficiently tidal forces can strip material away. The presence or absence of gas determines whether there will be bursts of star formation. And the environment matters too. A merger happening in isolation will proceed differently from one happening in a dense cluster. Some encounters are fleeting. Two galaxies might pass close enough to feel each other's gravity and exchange a bit of momentum, but not close enough to merge. These flyby interactions can still trigger star formation and distort galactic structures, but both galaxies escape afterward, continuing on their separate paths through space, perhaps scarred by the encounter, but still independent. Other encounters are fatal from the first moment. A small galaxy falling directly toward the center of a much larger one might be swallowed in a single pass, its stars scattered through the larger galaxy's halo, its core sinking rapidly to merge with the larger galaxy's nucleus. These are the quickest forms of galactic cannibalism, though even they take hundreds of millions of years to complete. Understanding these different types of interactions helps astronomers reconstruct the histories of the galaxies we see today. By looking at a galaxy's shape, its stellar populations, the motions of its stars, and the presence of features like tidal tails or stellar streams, we can often deduce its merger history. We can tell which galaxies have recently undergone mergers, which ones are currently merging, and which ones have been relatively undisturbed for billions of years. The Hubble Space Telescope and other powerful instruments have given us spectacular images of galaxies caught in various stages of merging. Some show two distinct spiral galaxies connected by bridges of stars. Others show wildly distorted shapes, galaxies that have been pulled into peculiar configurations by tidal forces. Still others show the aftermath, elliptical galaxies with multiple bright cores, revealing that they formed from the recent merger of several smaller systems. Computer simulations have been crucial for understanding galaxy mergers. Modern supercomputers can model the collision of two galaxies. Following the gravitational interactions of billions of simulated particles over billions of simulated years. These simulations have taught us that mergers are not random, chaotic events, but follow predictable patterns. The shapes of tidal tails, the rates of star formation, the final configuration of the merged galaxy, all these can be predicted given information about the initial conditions. The mechanics of tidal disruption. To truly understand galactic cannibalism, we need to understand tidal forces, the subtle but powerful effect that lies at the heart of how galaxies tear each other apart. Tidal forces are one of the most fundamental phenomena in gravitational physics, and they play out on every scale in the universe, from planets and moons to galaxies and galaxy clusters. The basic principle is simple. Gravity weakens with distance. If you have an extended object, like a moon or a galaxy, the side closer to a massive body experiences stronger gravitational pull than the far side. This difference in gravitational pull across the object creates a stretching force. On Earth, this is what creates ocean tides, as the moon's gravity pulls more strongly on the water on the near side of Earth than on Earth's center, and more strongly on Earth's center than on the far side. In the context of galaxies, tidal forces operate on a stupendous scale. Imagine a dwarf galaxy orbiting the Milky Way. As it approaches our galaxy, the stars on the dwarf galaxy's near side feel a stronger pull toward the Milky Way than the stars on the far side. This differential force begins to stretch the dwarf galaxy along the line connecting it to the Milky Way. At the same time, there's a squeezing force perpendicular to this line, compressing the dwarf galaxy in the other directions. At first, the dwarf galaxy can resist these tidal forces. Its own internal gravity holds it together. But as it gets closer to the Milky Way, the tidal forces grow stronger. They scale with the inverse cube of distance, which means they increase very rapidly as the galaxies approach each other. Eventually, the tidal forces exceed the dwarf galaxy's self-gravity, and it begins to be pulled apart. The disruption doesn't happen all at once. It's a gradual process. First, the outermost stars, which are most weakly bound to the dwarf galaxy, are stripped away. They form what astronomers call tidal tails, two streams of stars extending from opposite sides of the dwarf galaxy. One stream, called the leading tail, stretches out ahead of the dwarf galaxy along its orbit. The other, the trailing tail, extends behind it. Why two tails? It comes down to orbital mechanics. The stars that are pulled away from the dwarf galaxy on the side facing the Milky Way are pulled into slightly lower orbits. They move a bit faster than the dwarf galaxy's center, so they gradually pull ahead. The stars stripped from the far side end up in slightly higher orbits, moving a bit slower, so they fall behind. Over time, these streams stretch out along the dwarf galaxy's orbital path, wrapping around the larger galaxy like ghostly ribbons. These stellar streams are some of the most beautiful structures in astronomy. They're incredibly faint, containing relatively few stars spread across enormous distances. But deep imaging surveys like those conducted with the Sloan Digital Sky Survey and the ongoing Gaia mission have revealed dozens of stellar streams in the Milky Way's halo. Each one is the remnant of a dwarf galaxy or globular cluster that was torn apart by tidal forces, sometimes billions of years ago. The streams are not static. As they orbit the Milky Way, they continue to spread out and disperse. The stars gradually mix with the surrounding halo population. Over billions of years, a stellar stream can be completely dissolved, its stars scattered throughout the galaxy. But while they last, these streams are incredibly valuable to astronomers because they provide information about the Milky Way's gravitational field and dark matter distribution. Here's why. The shape and motion of a stellar stream depend on the gravitational potential through which it's moving. If there are clumps of dark matter in the halo, they will perturb the stream, creating gaps or wiggles. If the dark matter halo has a particular shape, say more elongated than spherical, the streams will align with that shape. By mapping stellar streams in detail and studying their kinematics, Astronomers can infer properties of the dark matter halo that would be impossible to measure any other way. The process of tidal disruption affects not just stars, but also gas. In fact, gas is stripped even more easily than stars because it can experience ram pressure, a kind of pressure created when the galaxy moves through the hot, diffuse gas that fills the space between galaxies in clusters. A galaxy moving through a cluster at high speed experiences a wind, much like a car moving through air, and this wind can blow gas out of the galaxy. The combination of tidal stripping and ram pressure stripping can very efficiently remove gas from a galaxy. This has profound implications for star formation. Without gas, a galaxy cannot form new stars. Many of the small, red, gas-poor galaxies we see in dense galaxy clusters probably lost their gas through these stripping processes. They were once blue, star-forming spirals or irregulars, but encounters with larger galaxies and passage through the hot cluster gas stripped away their star-forming material, transforming them into the quiescent systems we see today. The detailed structure of tidal tails depends on the orbit of the satellite galaxy. If the satellite is on a prograde orbit, moving in the same direction as the rotation of the larger galaxy's disk, the tails tend to be narrower and more tightly wound. If it's on a retrograde orbit, moving opposite to the disk rotation, the tails can be broader and more diffuse. The angle of the orbit relative to the galaxy's disk also matters, with highly inclined orbits producing different structures than orbits close to the disk plane. Computer simulations have shown that the formation of tidal tails is an inevitable consequence of close encounters between galaxies of different masses. You cannot avoid creating these structures. The physics is too fundamental. Whenever you have an extended object in a non-uniform gravitational field, tidal forces will pull it apart. This means that stellar streams should be ubiquitous in the universe, and indeed, observations confirm this. Almost every large galaxy we've looked at carefully shows evidence of stellar streams in its halo. Some of the most spectacular examples of tidal tails come from major mergers. The mice galaxies, so named because they look like two mice with long tails, show dramatic tidal tails extending over 300,000 light-years from each galaxy. The antennae galaxies, named for their long, antenna-like projections, are another famous example. These systems are caught in the act of merging, and their tidal tails light up with the blue glow of newly formed stars, created when gas clouds in the tails collapsed under their own gravity. In some cases, dense knots of material in tidal tails can become gravitationally bound, forming what are called tidal dwarf galaxies. These are small galaxies born from the debris of larger galaxy interactions. They contain gas and young stars, and they orbit in the outskirts of the merged system. Tidal dwarf galaxies are interesting because they appear to contain little or no dark matter, unlike normal dwarf galaxies. They're made purely of baryonic matter pulled from the disks of the parent galaxies, material that didn't contain much dark matter to begin with. The study of tidal disruption extends beyond galaxies to star clusters as well. Globular clusters orbiting through a galaxy's disk can be tidally disrupted. Their stars slowly stripped away over billions of years. The result is a stellar stream associated with the cluster's orbit. Several such streams have been identified in the Milky Way, including streams associated with the globular clusters Palomar 5 and NGC 5466. Understanding tidal disruption helps us understand how galaxies grow through cannibalism. Every stellar stream represents a past meal, a smaller system that was consumed by the larger galaxy. By cataloging and studying these streams, we can reconstruct the merger history of galaxies, counting how many satellites they've consumed and when those mergers occurred. It's like cosmic archaeology, piecing together the past from the fossil evidence scattered through galactic halos. The Milky Way's cannibalistic history. Our home galaxy, the Milky Way, is far from innocent when it comes to galactic cannibalism. In fact, the Milky Way is built from the wreckage of dozens, perhaps hundreds, of smaller galaxies that it has consumed over the past 13 billion years. The evidence for this cosmic violence is written in the stars themselves, in their motions, their chemical compositions, and their locations within the galactic halo. One of the most significant mergers in the Milky Way's history occurred about 10 billion years ago, when our galaxy was still young and actively forming. This event is called the Gaia-Sausage-Enceladus merger, named after the European Space Agency's Gaia satellite that helped identify it and the peculiar sausage-like distribution of stars in velocity space associated with it. The Gaia-Sausage-Enceladus was a dwarf galaxy roughly a quarter the mass of the proto-Milky Way at the time. When it collided with our galaxy, it wasn't a gentle encounter. The dwarf galaxy plunged almost head-on into the young Milky Way, its stars scattering through the inner halo and bulge. The merger was violent enough to significantly heat up the Milky Way's disk, puffing it up and adding a significant amount of orbital energy to its stars. We can identify stars from the Gaia-Sausage-Enceladus today by their unusual orbits and their chemical compositions. These stars move on highly elliptical radial orbits, plunging through the galactic center and then swinging out to large distances. Their chemistry is also distinctive. They formed in a different galaxy, under different conditions, and so they have a different mix of elements than stars born in the Milky Way. By identifying thousands of stars with these characteristics, astronomers have been able to reconstruct the properties of the original dwarf galaxy and understand how its merger affected the Milky Way's structure. The Gaia-Sausage-Enceladus merger may have contributed as much as 80% of the Milky Way's inner stellar halo. That's an astonishing fraction. It means that when you look at stars in the halo above and below the Milky Way's disk, there's a good chance you're looking at immigrant stars, stars born in another galaxy billions of years ago that are now part of our own. But the Gaia-Sausage-Enceladus was not the only merger in the Milky Way's history. Astronomers have identified evidence for several other significant accretion events. There's the Helmy Stream, discovered in '99, the remnant of a dwarf galaxy that merged with the Milky Way about 6 to 9 billion years ago. There's the Sagittarius Stream, which we'll discuss in more detail shortly. There's evidence for a merger called the Kraken, which may have occurred even earlier than Gaia-Sausage-Enceladus. And there are numerous smaller events, dwarf galaxies containing just a few million stars that were consumed by the Milky Way and left behind faint stellar streams in the halo. More recent research, published in 2024, identified another significant merger event that occurred surprisingly recently in cosmic terms, just 2.7 billion years ago. This merger, called the Virgo radial merger, created wrinkles in the Milky Way's stellar disk that are still visible today. Yes, wrinkles. Just as our skin develops wrinkles as we age, the Milky Way's disk shows ripples and corrugations that formed when a dwarf galaxy collided with it. These wrinkles are not evenly distributed across the disk. They're strongest in certain regions, and by studying their pattern, astronomers can deduce the properties of the dwarf galaxy that caused them. The merger must have occurred relatively recently because older wrinkles would have been smoothed out by the internal dynamics of the galaxy. It's somewhat counterintuitive, but the Milky Way actually becomes less wrinkly as it ages, making it a sort of cosmic Benjamin Button. The most dramatic ongoing example of galactic cannibalism in the Milky Way involves the Sagittarius dwarf elliptical galaxy. This system was discovered only in 1994, despite being one of the closest neighboring galaxies to the Milky Way. The reason it remained hidden for so long is that it's on the far side of the galaxy from our perspective, obscured by the dense star fields and dust clouds of the Milky Way's bulge. The Sagittarius dwarf is being absolutely shredded by the Milky Way. As it orbits, tidal forces are pulling it apart, stripping away its stars and stretching them into a long stream that wraps around the Milky Way multiple times. The Sagittarius stream is now known to loop around our galaxy at least 3 times, forming a complex structure in the halo. The dwarf galaxy itself is disintegrating, losing mass with each orbit. Eventually, perhaps in another billion years, it will be completely dissolved, its stars fully absorbed into the Milky Way's halo. What makes the Sagittarius merger particularly interesting is that we can see it happening right now. We're not looking at the aftermath of an ancient collision. We're watching a galaxy die, being torn apart in real time, or as close to real time as makes sense on galactic timescales. By studying the Sagittarius stream in detail, astronomers can learn about the process of tidal disruption, test models of the Milky Way's gravitational potential, and even constrain the properties of dark matter. The Large and Small Magellanic Clouds are another case of ongoing cannibalism, though this process is at an earlier stage. These 2 dwarf, irregular galaxies are visible from the southern hemisphere as fuzzy patches of light. They've been known since ancient times, and were named after the explorer Ferdinand Magellan, whose crew observed them during their circumnavigation of the globe in the early 16th century. For a long time, astronomers thought the Magellanic Clouds were long-term satellites of the Milky Way, bound systems that had been orbiting our galaxy for billions of years. But recent measurements of their motions, particularly from the Gaia satellite, suggest something different. They might be on their first close passage around the Milky Way. They may have been wandering through an intergalactic space for billions of years, and only recently fallen into the Milky Way's gravitational influence. If this is true, it changes our understanding of their future. They're moving fast enough that they might eventually escape the Milky Way's gravity, becoming independent galaxies once again. Or they might not. The data is still uncertain, and there are different interpretations. But one thing is clear. Even if they do escape this time, they're losing mass to tidal stripping. There's already evidence of a stream of gas trailing behind the Magellanic Clouds, called the Magellanic Stream, stretching across more than 100 degrees of the sky. This stream contains about 2 billion times the mass of the Sun in hydrogen gas, stripped from the clouds by a combination of tidal forces and ram pressure from the Milky Way's hot halo gas. Over time, whether in this orbit or a future one, the Magellanic Clouds will likely be consumed by the Milky Way. Their stars will be scattered into our halo. Their gas will fuel star formation in the Milky Way's disk. And billions of years from now, the only evidence of their existence might be a stellar stream, a faint river of stars orbiting through the halo, slowly dispersing until even that evidence fades away. By studying all these stellar streams, these remnants of consumed galaxies, astronomers have learned that the Milky Way has grown significantly through cannibalism. Perhaps 25 to 30% of the Milky Way's current stellar mass came from mergers rather than being formed in place. Our galaxy is truly a composite structure built from the ruins of many smaller systems. And this growth through cannibalism isn't finished. The Milky Way continues to consume satellites. It continues to grow. In some sense, the galaxy you live in today is not the same galaxy that existed when the dinosaurs walked the Earth, and it won't be the same galaxy billions of years from now. It's a dynamic, evolving structure, constantly being reshaped by the slow process of accreting and absorbing smaller systems. There's something almost poetic about this. The stars in the Milky Way's halo, those ancient wanderers that formed in other galaxies, carry with them memories of the worlds we will never see. Galaxies that existed billions of years ago, that had their own distinct structures and histories, are now part of the Milky Way only as scattered populations of stars. Their original forms have been erased, but their legacy lives on in the motions and chemistry of their former members. Starburst galaxies and the aftermath. One of the most spectacular consequences of galactic cannibalism is the creation of starburst galaxies. Systems undergoing such rapid star formation that they can form the equivalent of 100 or even 1,000 suns every year. To put that in perspective, the Milky Way today forms about 2 or 3 new stars per year. A starburst galaxy is creating stars at rates that dwarf anything happening in normal, quiet galaxies. The trigger for these intense bursts of star formation is the collision of gas clouds during galaxy mergers. Stars in galaxies are separated by such vast distances that they almost never collide, but gas clouds are much larger and more diffuse. When two galaxies merge, their gas clouds definitely do collide, and when they do, the results are dramatic. Imagine 2 giant molecular clouds, each containing millions of solar masses of hydrogen and helium, colliding at hundreds of kilometers per second. The collision creates a shock wave, a region where the gas is suddenly compressed to much higher densities than normal. This compression heats the gas initially, but it also triggers instabilities that cause portions of the cloud to collapse under their own gravity. Once collapse begins, it feeds on itself. As gas falls inward, it releases gravitational potential energy, heating the central regions. When the core gets hot and dense enough, nuclear fusion ignites, and a new star is born. But the process doesn't stop there. The radiation and stellar winds from newly formed massive stars compress nearby regions of the cloud, triggering more collapse, more star formation. Supernovae from short-lived massive stars add even more energy, creating a complex cycle of triggered star formation. In a major merger between two gas-rich spiral galaxies, this process can convert a substantial fraction of the galaxy's gas into stars in just a few 100 million years. The result is a galaxy blazing with the light of billions of newly formed stars. The massive stars, hot and blue, dominate the visible light output, giving starburst galaxies their characteristic blue color. Ultraviolet radiation from these stars ionizes surrounding hydrogen gas, creating vast emission nebulae that glow red with the light of excited hydrogen atoms. But this intense activity comes at a cost. Star formation on such a scale cannot be sustained for long. The massive stars that dominate a starburst have lifetimes of just a few million years. When they explode as supernovae, they blast enormous amounts of energy into the surrounding gas. Multiple supernovae occurring in the same region create what's called a superbubble, a vast cavity blown out of the interstellar medium by the combined force of dozens or hundreds of stellar explosions. These superbubbles can grow to thousands of light-years in diameter. They punch through the galactic disk, venting hot gas into the halo in powerful galactic winds. This process, called feedback, is one of the ways galaxies regulate their own star formation. By expelling gas from the galaxy, supernova-driven winds reduce the amount of material available for future star formation. In the most intense starbursts, the feedback can be so powerful that it essentially shuts down star formation entirely, blowing most of the remaining gas out of the galaxy. The antennae galaxies provide a beautiful example of a starburst in action. These two spiral galaxies began colliding about 600 million years ago, and are now in the midst of their most intense interaction. Hubble Space Telescope images of the antennae reveal thousands of bright blue star clusters scattered throughout the galaxy, particularly in the region where the two disks overlap. Each cluster contains thousands or millions of young stars, all formed in the last few million years. The antennae are forming stars at a rate roughly 100 times higher than the Milky Way. This burst of star formation will continue for perhaps another 100 million years, until the gas is exhausted or blown away. Eventually, the two galaxies will merge completely, probably forming an elliptical galaxy. The star formation will shut down, and the system will fade from blue to red as the massive blue stars die and are replaced by the longer-lived red and yellow stars. Another famous starburst system is M82, the Cigar Galaxy. This irregular galaxy is undergoing a burst of star formation triggered by a close encounter with the nearby larger galaxy M81. The starburst is concentrated in the central regions of M82, where the gas compression was strongest. The rate of star formation is so high that supernovae are exploding roughly every 10 years. The combined effect of all these supernovae has driven a powerful wind out of the galaxy's disk, visible in images as red filaments of ionized gas streaming perpendicular to the disk. Starburst galaxies are not just interesting in their own right, they also play an important role in galactic evolution. The bursts of star formation triggered by mergers help convert gas into stars more efficiently than would happen in isolation. This means that galaxies that undergo mergers end up with higher stellar masses than galaxies that evolve in isolation. This is one of the ways that large galaxies grow. The supernovae that result from starburst activity also enrich the interstellar medium with heavy elements. Every supernova ejects several solar masses of material, much of it in the form of elements like oxygen, carbon, nitrogen, silicon, and iron. These elements, forged in the cores of massive stars, are scattered into space where they mix with the interstellar gas and become incorporated into the next generation of stars and planets. Without supernovae, and without the starburst activity triggered by galaxy mergers, the universe would be a much different place. The gas clouds from which stars form would remain almost pure hydrogen and helium, as they were in the early universe. There would be no rocky planets, no organic chemistry, no possibility of life as we know it. Galactic cannibalism, violent though it may be, is actually essential for creating the chemical diversity that makes complex structures possible. There's also evidence that starburst activity can affect the supermassive black holes at galaxy centers. During a merger, gas is funneled toward the centers of the galaxies, where it can be captured by the black holes. As gas spirals into a black hole, it heats up and emits enormous amounts of energy in the form of light, X-rays, and other radiation. This creates what's called an active galactic nucleus, or AGN. AGN can be so luminous that they outshine entire galaxies. The most extreme examples, called quasars, can be visible across the entire observable universe. Most AGN activity occurred in the early universe when galaxy mergers were more common and gas was more abundant. Today, most supermassive black holes are relatively quiet, accreting material slowly, if at all. But when galaxies merge, the black holes can wake up, at least temporarily, becoming active again as they feast on gas funneled to them by the merger. The relationship between starburst activity, AGN activity, and galaxy mergers is complex and still being worked out. It appears that mergers can trigger both star formation and black hole growth, though not necessarily at the same time. The starburst might occur early in the merger, when gas clouds first collide, while the AGN phase might come later, after gas has had time to lose angular momentum and spiral into the center. Eventually, both processes shut down. The starburst ends when the gas is exhausted or expelled. The AGN phase ends when the black hole runs out of material to accrete. What's left is a galaxy that has converted much of its gas into stars, grown a more massive central black hole, and transformed from a star-forming system to a quiescent one. This transformation, from blue star-forming galaxy to red quiescent galaxy, is one of the key processes in galaxy evolution, and mergers play a major role in driving it. The future, Milky Way and Andromeda. The most dramatic act of galactic cannibalism in the local group has not yet occurred, but it's already inevitable. The Milky Way and the Andromeda galaxy are on a collision course. Right now, as you listen to this, Andromeda is moving toward us at about 110 kilometers per second. That's roughly 250,000 miles per hour. In cosmic terms, it's not particularly fast, but given enough time, even this modest speed will close the 25 million light-years that currently separate us. The collision will begin in about 4.5 billion years. By begin, we mean the first close passage, when the two galaxies' outer regions start to interpenetrate. The actual merger, the final coalescence into a single system, will take several billion years after that. So, we're looking at an event roughly 6 to 7 billion years from now before the merged galaxy settles into its final form. What will this collision look like? Astronomers have run numerous computer simulations of the Milky Way Andromeda merger, inputting the best available measurements of both galaxies' masses, sizes, velocities, and orientations. While the exact details vary depending on the initial conditions, the general outcome is consistent across most simulations. The first passage will be the most dramatic from an observational standpoint, if there were any observers to witness it. The two galaxies will sweep past each other, their stars never actually colliding, but their gravitational fields creating havoc in both systems. Tidal forces will distort both galaxies, pulling out great arcing tidal tails. The spiral structures will be disrupted, their neat spiral arms twisted and broken. If humans, or whatever our descendants might be, are still around at that time, the night sky will be absolutely spectacular. Andromeda, which today appears as a faint smudge visible to the naked eye under dark skies, will dominate the heavens. As it approaches, it will grow larger and brighter, eventually stretching across a significant portion of the sky. During the closest approach, it will be a magnificent sight, a great wheel of light filling the darkness, its spiral arms clearly visible even to the naked eye. But there is no need to worry about the safety of Earth or the solar system. Despite the violence of a galactic collision, individual stars are almost never affected. Remember, stars are separated by such vast distances that the probability of a collision, or even a close encounter, is essentially zero. The solar system will simply find itself in new surroundings, perhaps in a different part of the merged galaxy, but otherwise unchanged. There is, however, one thing that might affect us: the Sun itself. In 4.5 billion years, the Sun will be significantly more luminous than it is today. As main sequence stars age, they slowly heat up. The Sun's luminosity has increased by about 30% since it formed 4.6 billion years ago, and it will increase by another 40% or so over the next 4 to 5 billion years. By the time the Milky Way and Andromeda collide, Earth will likely be too hot for liquid water to exist on its surface. The oceans will have evaporated, the atmosphere will be inhospitable, and Earth will have become a Venus-like world. So, while the galactic collision won't directly harm us, the Sun's own evolution will have already made Earth uninhabitable. If humanity still exists at that time, we will need to have moved to other star systems, perhaps orbiting cooler, longer-lived stars than the Sun. From those new vantage points, our distant descendants might look up and watch the greatest show in the cosmos: two spiral galaxies locked in a slow cosmic dance, merging over billions of years. After the first passage, the two galaxies will continue moving apart, but they'll have lost orbital energy to the interaction. they'll reach a maximum separation, perhaps 1 million light-years or more, and then fall back together. The second passage will be closer and more destructive than the first. More tidal tails will form. More stars will be scattered into the merged system's halo. The central regions will begin to interpenetrate more deeply. This back and forth can continue for several cycles, but eventually, perhaps after 3 or 4 passes, the two galaxies will lose enough energy that they can't pull apart anymore. The final merger will begin. The cores of both galaxies, each containing a supermassive black hole, will spiral toward each other through a process called dynamical friction. Dynamical friction is a subtle effect, but it's crucial for understanding how galaxy mergers proceed. As a massive object, like a galaxy core, moves through a sea of stars, it gravitationally attracts stars behind it. These stars speed up and catch up, creating an overdensity of stars behind the moving object. This overdensity exerts a gravitational pull, like a wake, that slows the moving object down. Over billions of years, dynamical friction removes enough orbital energy that the two galaxy cores spiral together and merge. When the two cores finally merge, their supermassive black holes will merge as well. The Milky Way's black hole, Sagittarius A, has a mass of about 4.1 million solar masses. Andromeda's black hole is significantly larger, perhaps 100 million solar masses or more. When they merge, they'll form a single supermassive black hole with a combined mass of over 100 million solar masses. The merger of two supermassive black holes is one of the most energetic events imaginable. As they spiral together in the final moments before merging, they'll emit powerful gravitational waves, ripples in space-time itself traveling at the speed of light. These gravitational waves will carry away energy, causing the black holes to spiral together faster and faster until they merge in a final burst of gravitational radiation. We won't be able to detect these gravitational waves with current technology. They'll be at too low a frequency. But future space-based gravitational wave detectors, like the proposed LISA mission, might be able to observe such events, giving us an entirely new way to study galactic mergers. The final product of the Milky Way Andromeda merger will be a giant elliptical galaxy. The simulations show that the merger will largely destroy both galaxies' spiral structures. The orderly rotation of the disks will be converted into random motion, creating the chaotic stellar orbits characteristic of elliptical galaxies. Some astronomers have given this future merged galaxy a name, Milky, a somewhat clumsy portmanteau of Milky Way and Andromeda. Milky will be one of the largest galaxies in the local group, containing perhaps 1 trillion stars. It will be a fairly isolated system. Most of the other galaxies in the local group are small dwarf galaxies that will either be consumed by Milky or remain as small satellites orbiting it. The galaxy will be a reddish color, dominated by older yellow and red stars. Star formation will have largely ceased, most of the gas having been converted into stars during the merger or expelled from the galaxy by feedback processes. And there, Milky will remain, an aging giant elliptical drifting through the cosmos, slowly evolving as its stars age and die, occasionally consuming a small satellite but otherwise quiet and quiescent. It's a peaceful ending to a violent collision, the final chapter in the story of two great spiral galaxies that once graced the cosmos with their beauty. Monster elliptical galaxies. At the centers of rich galaxy clusters lurk some of the largest galaxies in the universe. These are the giant elliptical galaxies, sometimes called brightest cluster galaxies or CD galaxies. They're absolutely enormous, containing trillions of stars and extending across hundreds of thousands or even millions of light years. And they are almost certainly the products of galactic cannibalism taken to its extreme. A typical giant elliptical might have grown through dozens or even hundreds of mergers. It sits at the bottom of its galaxy cluster's gravitational potential well, meaning that other galaxies naturally fall toward it. Over billions of years, it has consumed galaxy after galaxy, growing ever larger with each meal. The evidence for this cannibal history is written in the structure of these galaxies. Many giant ellipticals show multiple bright cores or nuclei, the remnants of galaxies that fell in relatively recently and haven't yet been fully digested. Each nucleus represents a galaxy core that was once independent but is now being slowly dissolved into the larger structure. The process of building a giant elliptical through mergers is called hierarchical growth, and it's a key prediction of the cold, dark matter model of structure formation. In this model, small galaxies form first, then merge to form larger ones. The largest galaxies, like giant ellipticals, form last, through the coalescence of many smaller systems. The more massive the galaxy, the longer its assembly time. Computer simulations have shown that you can build galaxies with the properties of observed giant ellipticals by simulating the merger history of galaxy clusters. You start with a population of smaller galaxies and let gravity do its work. Galaxies fall into the cluster, orbit within it, and occasionally merge. The largest galaxy, sitting at the center, grows with each merger. After several billion years of simulated time, you end up with a central giant elliptical that looks remarkably like what we observe. These simulations also make predictions about the stellar halos of giant ellipticals. The stars stripped from infalling galaxies don't all end up in the main body of the giant elliptical. Many are scattered into a diffuse stellar halo that can extend millions of light years from the galaxy's center. This halo is incredibly faint, with surface brightnesses so low that detecting it requires extremely deep imaging. But recent observations have confirmed that these extended halos exist exactly as predicted by the simulations. The stellar populations in giant ellipticals also tell a story of multiple mergers. When astronomers analyze the spectra of these galaxies, they find that different regions have different chemical compositions. Some regions are rich in certain elements, others in different elements. This chemical inhomogeneity is a fossil record of the galaxy's merger history. Each consumed galaxy brought its own stars, with their own chemical fingerprints, and these fingerprints remain visible even billions of years after the merger. One of the most interesting aspects of giant ellipticals is their central supermassive black holes. Because these galaxies have grown through multiple mergers, their black holes have also grown through multiple mergers. Each time, too, galaxies merge. their black holes eventually merge as well, creating a progressively more massive black hole at the center. The supermassive black holes in giant ellipticals are among the most massive in the universe, with masses that can exceed 10 billion solar masses. These are truly monstrous objects, containing more mass than some entire galaxies, and they exert a profound influence on their host galaxies. As gas falls into these massive black holes, it releases enormous amounts of energy. This energy, in the form of radiation, jets, and winds, can heat the gas in and around the galaxy, preventing it from cooling and forming new stars. This process, called AGN feedback, is thought to be one of the main reasons why giant ellipticals are so red and dead. They have plenty of gas, but that gas is too hot to collapse and form stars because the central black hole keeps heating it. The relationship between supermassive black holes and their host galaxies is still being worked out, but there's strong evidence that the black hole's mass is correlated with properties of the galaxy's bulge. This correlation, known as the M-sigma relation, suggests that black holes and their host galaxies co-evolve. Mergers drive this coevolution by simultaneously feeding the black hole and building up the stellar population of the galaxy. Giant ellipticals are not static. Even after they've grown to enormous sizes, they continue to consume smaller galaxies. Astronomers have observed dwarf galaxies falling into giant ellipticals, being tidally disrupted, and having their stars added to the giant's halo. This slow, ongoing cannibalism means that giant ellipticals are still growing today, albeit much more slowly than in the past when galaxy mergers were more common. The Virgo cluster, the nearest large galaxy cluster to us, provides an excellent laboratory for studying giant ellipticals. At its center lies M87, a giant elliptical that contains about 1 trillion solar masses in stars. M87 has been consuming galaxies for billions of years, and it's still doing so today. Deep imaging of M87 has revealed numerous stellar streams in its halo, each one the ghost of a devoured dwarf galaxy. M87 is also famous for its central supermassive black hole, the first black hole ever imaged directly by the Event Horizon Telescope in 2000. With a mass of about 6.5 billion solar masses, this black hole is one of the most massive known. It powers a jet of material that extends for thousands of light-years from the galaxy, a visible manifestation of the black hole's influence on its surroundings. The study of giant ellipticals helps us understand the end state of galaxy evolution. In the densest regions of the universe, where galaxies are packed closely together, the ultimate fate of most galaxies is to be consumed by the central giant elliptical. This is galactic cannibalism writ large, the culmination of billions of years of hierarchical structure formation. The result is a handful of massive, ancient galaxies, the dominant members of their galaxy clusters, built from the remnants of countless smaller systems. Observing galactic cannibalism. How do astronomers actually observe galactic cannibalism? Since these events unfold over billions of years, we can't watch a single galaxy merger from start to finish. Instead, we have to piece together the story from snapshots, from observations of many different galaxies caught in various stages of interaction, and from the fossil evidence of past mergers preserved in today's galaxies. One of the primary ways to detect ongoing mergers is through morphology, the shape and structure of galaxies. When galaxies interact gravitationally, their shapes become distorted. Normal spiral galaxies have symmetric, orderly structures, but merging galaxies look disturbed. They have tidal tails, bridges of stars connecting the two galaxies, asymmetric spiral arms, warped disks, and other peculiarities. The Hubble Space Telescope has been particularly valuable for studying galaxy mergers because of its high resolution. Even distant galaxies, billions of light-years away, can be resolved into enough detail to see tidal features. The Hubble Deep Fields, ultra-deep images of small patches of sky, revealed that peculiar and disturbed galaxies were much more common in the distant past than they are today. This makes sense because the universe was denser in the past, and galaxies were closer together and more likely to interact. Another way to identify mergers is through stellar streams. As we've discussed, when a small galaxy is tidally disrupted, its stars are stretched into a stream that orbits through the larger galaxy's halo. These streams are very faint, but deep imaging surveys can detect them. The Sloan Digital Sky Survey, for example, has mapped stellar streams throughout the Milky Way's halo, each one the remnant of a past merger. The Gaia satellite has revolutionized the study of stellar streams by providing precise positions and velocities for over 1 billion stars in the Milky Way. With this data, astronomers can identify groups of stars that are moving together through space, even if they're scattered across the sky. Many of these moving groups turn out to be stellar streams, allowing astronomers to trace the orbits of disrupted satellites and reconstruct the Milky Way's merger history in unprecedented detail. Chemical signatures also reveal past mergers. Every star carries a chemical fingerprint based on the gas from which it formed. Stars born in different galaxies have different chemical compositions. Because the star formation histories and chemical enrichment processes were different. By measuring the chemical compositions of many stars in a galaxy's halo, astronomers can often identify distinct populations that likely originated in different galaxies that were later consumed. Computer simulations play a crucial role in interpreting observations. Modern supercomputers can simulate the collision of two galaxies in exquisite detail, following billions of particles representing stars and dark matter over billions of years of simulated time. By comparing these simulations to observations, astronomers can test whether their understanding of galactic dynamics and merger physics is correct. The simulations make specific predictions. For example, they predict the shapes and longevities of tidal tails, the rates of star formation during mergers, the final morphologies of merger remnants, and the properties of stellar streams. When observations match these predictions, it gives us confidence that we understand the underlying physics. When observations don't match predictions, it tells us we need to revise our models. Spectroscopy is another powerful tool. By splitting the light from a galaxy into its component wavelengths, astronomers can learn about the galaxy's stellar populations, its star formation history, its chemical composition, and the motions of its stars and gas. Galaxies undergoing mergers show distinctive spectroscopic signatures. Broad emission lines from ionized gas, indicating vigorous star formation. Absorption lines that show multiple velocity components, revealing the presence of stars from different progenitor galaxies, and sometimes signs of an active galactic nucleus, fed by gas funneled to the center during the merger. Infrared observations have proven particularly valuable for studying mergers. When galaxies collide and trigger intense star formation, much of the radiation from young stars is absorbed by dust and re-emitted in the infrared. Infrared telescopes like Spitzer and Herschel have revealed populations of luminous infrared galaxies, systems undergoing intense star formation triggered by mergers. These galaxies can be so enshrouded in dust that they're barely visible in optical light, but they blaze in the infrared. Radio observations reveal yet another aspect of mergers. Hydrogen gas emits radio waves at a specific frequency, the famous 21 centimeter line, allowing radio telescopes to map the distribution and motion of gas in and around galaxies. Radio observations have revealed enormous streams of hydrogen gas associated with merging galaxies, as well as tidal tails and debris fields that are invisible in optical light. The study of galactic cannibalism has also benefited from surveys that observe thousands or millions of galaxies. Large surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Legacy Survey of Space and Time from the Vera Rubin Observatory provide statistically significant samples of merging galaxies. By studying large numbers of mergers at different stages and in different environments, astronomers can understand how common mergers are, how they depend on galaxy mass and environment, and how they've evolved over cosmic time. One particularly interesting technique is galactic archaeology, the practice of using the properties of stars today to reconstruct the histories of their host galaxies. Just as archaeologists piece together ancient human history from artifacts and ruins, galactic archaeologists piece together galaxy formation histories from stellar populations, chemical abundances, and stellar orbits. This technique has been especially powerful in the Milky Way, where we can study individual stars in detail. As observational techniques improve, we're able to detect fainter and fainter merger signatures. What once appeared to be a smooth, featureless galaxy halo often turns out, in deeper images, to be filled with faint streams, shells, and other substructures. Almost every large galaxy we've looked at carefully shows evidence of past mergers, confirming that galactic cannibalism is a fundamental process in galaxy evolution. The bigger picture. Galactic cannibalism is not just a curious phenomenon happening to individual galaxies. It's a fundamental process that has shaped the structure of the universe on the largest scales. To understand its true significance, we need to step back and look at the bigger picture of cosmic evolution. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were tiny variations in density, quantum fluctuations from the first moments of existence amplified by cosmic inflation. But these variations were only about 1 part in 100,000. Over time, however, gravity amplified these tiny differences. Regions that were slightly denser attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to their surroundings, becoming voids. This process created a cosmic web, a large-scale structure of matter that fills the universe. The web consists of dense nodes where galaxy clusters form, filaments connecting these nodes, and vast, empty voids between them. Galaxies form at the intersections of filaments and in the densest nodes. And once they form, they begin to interact gravitationally with their neighbors. In this context, galactic cannibalism is simply the natural consequence of gravity operating over billions of years. Galaxies in overdense regions fall toward each other, collide, and merge. The more massive a region, the more mergers occur within it. This is why the largest galaxies are found in galaxy clusters. They've had more opportunities to grow through cannibalism. The frequency of galaxy mergers has changed over cosmic time. In the early universe, when galaxies were younger and closer together, mergers were far more common. Observations of distant galaxies, whose light has taken billions of years to reach us, show that distorted, irregular, and actively star-forming galaxies were the norm in the past. Perhaps 25% or more of galaxies were involved in mergers at any given time. Today, mergers are less common. The universe has expanded. Galaxies are farther apart on average, and most of the easy mergers have already happened. Still, about 5 to 10% of nearby galaxies show signs of recent or ongoing mergers. And in dense galaxy clusters, where galaxies remain close together, mergers continue to occur frequently. The role of dark matter in galactic cannibalism can not be overstated. Dark matter makes up about 85% of the matter in the universe, and it provides the gravitational scaffolding within which galaxies form and evolve. Every galaxy sits within a much larger dark matter halo. When galaxies merge, their dark matter halos merge as well, and it's primarily the gravity of these halos that drives the process. Simulations that include dark matter produce galaxies that look like real galaxies, with realistic sizes, shapes, and merger histories. Simulations without dark matter, or with modified theories of gravity that attempt to explain observations without invoking dark matter, generally fail to reproduce what we observe. This is one of the strongest pieces of evidence for the existence of dark matter. The process of hierarchical structure formation, where small structures merge to form larger ones, is a fundamental prediction of the cold dark matter model. Galactic cannibalism is hierarchical structure formation in action. Every large galaxy is built from smaller galaxies. Every galaxy cluster is built from smaller groups. The entire cosmic web is the result of billions of years of gravitational collapse and merger activity. Looking to the future, galactic cannibalism will continue to shape the universe, though at an ever-decreasing rate. As the universe expands, driven by dark energy, galaxy clusters will become more isolated from each other. Mergers will continue within clusters, but mergers between clusters will cease. Eventually, in the far future, hundreds of billions of years from now, most galaxies will have merged into single giant ellipticals within their local regions. But even this is not the end. Stars have finite lifetimes. The smallest, longest-lived red dwarf stars can shine for trillions of years, but eventually, even they will exhaust their fuel. Star formation will cease when galaxies run out of gas. And over unimaginably long timescales, the galaxies themselves will slowly evaporate, their stars ejected one by one through gravitational encounters until nothing remains but isolated black holes drifting through an ever darker, ever emptier universe. But that's a story for another night, a journey trillions of years into the future. For now, we live in a golden age of galaxies, when the universe is full of beautiful spirals, massive ellipticals, irregular dwarfs, and all the wonderful diversity of galactic forms. And we have the privilege of studying how these objects formed, how they evolve, and what forces shape them. Galactic cannibalism reminds us that even on the largest scales, the universe is dynamic and changing. Nothing is permanent. Galaxies that seem eternal and unchanging are actually in constant motion, constantly evolving, growing through mergers with smaller systems. What we see today is just one frame in a cosmic movie that has been playing for 13.8 billion years and will continue for trillions more. In a sense, we're made of recycled material from countless galactic mergers. The heavy elements in our bodies were forged in stars, but those stars formed from gas enriched by previous generations. Some of that gas might have originally been in a dwarf galaxy that was consumed by the Milky Way billions of years ago. We are, quite literally, the product of galactic cannibalism, built from atoms that have passed through multiple stars in multiple galaxies over cosmic time. There is something profound about that connection. When you look up at the stars, you're not just seeing distant lights. You're seeing a cosmic ecosystem, a universe where structures grow through consumption, where destruction leads to creation, where violence on unimaginable scales ultimately produces the conditions necessary for complexity, for planets, for life, for consciousness. The galaxies devouring each other across the cosmos are not separate from us. We are part of the same story, participants in the same grand cosmic drama. Closing thoughts. And so we come to the end of tonight's journey through the realm of galactic cannibalism. We've traveled from the mechanics of tidal disruption to the stellar streams in our own galaxy. We've watched computer simulations of galaxies colliding over billions of years. We've looked forward to the future collision between the Milky Way and Andromeda. We've explored how the largest galaxies in the universe grew through countless acts of cosmic consumption. And we've seen how astronomers piece together these violent histories from the faint traces left behind. The universe operates on scales so vast that even the most violent events unfold with a kind of patience. Galaxies don't crash together like cars on a highway. They dance around each other for billions of years, slowly spiraling together, their forms changing gradually, almost gracefully. Stars are flung into new orbits, gas clouds compressed into new stars. But the violence is spread across such enormous spaces and such immense timescales that from any individual perspective, it would seem almost peaceful. Perhaps that's the most remarkable thing about galactic cannibalism. These events that we describe with words like collision, destruction, and consumption are, from another perspective, simply the way the universe builds its largest and most complex structures. Without mergers, without this cosmic cannibalism, galaxies would be smaller, simpler, less diverse. The grand spiral galaxies we admire might never have formed. The heavy elements necessary for rocky planets and organic chemistry would be less abundant. The universe would be a quieter, emptier, less interesting place. If you've found tonight's exploration helpful, if it's given you something to think about as you drift towards sleep, consider liking this video and subscribing to the Sleepy Science Society. It helps other curious minds find their way here, one peaceful night at a time. As you rest tonight, remember that you are floating on a planet orbiting a star that sits within a galaxy built from the remnants of countless smaller galaxies. The iron in your blood was forged in a supernova billions of years ago, possibly in a galaxy that no longer exists as a separate entity. The atoms in your body have passed through stars, traveled through space, witnessed cosmic collisions, and somehow ended up here, assembled into a form capable of contemplating its own origins. The galaxies will continue their slow dance across the cosmos. The Milky Way will continue consuming its satellites, Andromeda will continue its approach, and billions of years from now, when our galaxy has merged with its neighbor and formed something new, the process will continue. Galaxies devouring galaxies, building ever larger structures, creating the conditions for new stars, new worlds, perhaps new forms of life to emerge and wonder at the universe. Sleep well, knowing that you're part of this grand cosmic story. Rest peacefully in the knowledge that the universe, for all its violence and vastness, has produced something as delicate and improbable as consciousness, as wonder as you. The stars turn above you. The galaxy rotates slowly through space, and you, a small arrangement of atoms briefly aware of itself, can close your eyes and drift into dreams, secure in the knowledge that the cosmos is unimaginably large, unimaginably old, and filled with wonders beyond counting. Good night.